Hi everybody, video number 2 is an introduction to uncertainties in A-level physics. It works for the IB as well at this level for our introduction, and later on we'll do videos about more difficult uncertainties and hopefully some advanced uncertainties including sines, cosines and logarithms. We need to talk about taking measurements. So when we take a measurement in physics, there's always an uncertainty. We don't know exactly what the value is that we're taking. It depends on a number of things. We're going to look at measurement uncertainties first. So when we have an instrument, there is some uncertainty associated with it. And we need to figure out what that is so we can express it in our answer. So we can say this is our best guess at the answer within these tolerances, plus or minus a bit. So we're going to look at readings first. So readings are when we have a single value measured from a scale. So examples of when we might take a reading include a thermometer or a measuring cylinder. These are things where the zero value is known. So we don't measure a zero value. Another good one is when we have, for example, a fiducial mark, which might look like a triangle of paper on a wire. So when you're doing Young's modulus calculations, what we were interested in our readings was the position of that mark on our scale. So that's just one reading. If we've got an analog scale, so for example a ruler or ammeter or voltmeter with a dial, we can measure to the nearest, well, it's plus or minus half the smallest scale division. Apologise for my writing. So if we've got a ruler and we're taking a reading and our ruler measures to the nearest 1 millimeter, then we don't know if it's exactly half that way or half that way. So we've got an uncertainty of half a scale division. So this reading here is slightly to the left of this mark, but still that's the closest mark we can read to. So we say it's here, but plus or minus half the smallest scale division. If we've got a digital scale, then we're going to use plus or minus 1 of the smallest scale division. So we don't know whether or not our meter, or an ammeter or voltmeter or any kind of digital scale, we don't know if it's rounding up, we don't know if it's rounding down. We've got no way to know. So we stick with 1 smaller scale division, plus or minus. So if we've got a reading like this in one place, that's good for using a thermometer or a measuring cylinder or a fiducial mark, and that's good for analog scales and digital scales. What if we were measuring the length of something? If we're measuring the length of something, then what we're doing is we're measuring the difference between two readings. So if we've got the difference between two readings, then so they were readings, these are measurements. If we've got a difference between two readings, we're going to have plus or minus 1 smallest scale division for an analog scale. Digital scales is always going to be a reading, but for an analog scale, when we're doing a measurement, it's the difference between two readings. So if, for example, I had a pencil against a ruler, I've got one reading here and one reading here. So in that case, we've got plus or minus half the smallest scale division in this position, and plus or minus half the smallest scale division in this position. So we've got plus or minus 1 smallest scale division. Okay, and we'll talk about why that is in the next video when we talk about combining uncertainties. If at any point you've got if you've got a piece of equipment with a tolerance stated, for example on a micrometer, or at least the ones we have at my college, we have a tolerance stated on the box of plus or minus 0.01 millimeter, and then for our vernier calipers we have a tolerance of plus or minus 0.02 millimeters. In those cases you use the tolerance stated. So always use a tolerance that's stated. If you've got for a range of repeated results, we have a slightly different method. So if the range of your repeated results is outside the tolerance of your equipment, or it's bigger than half the smallest scale division, then what we're going to use is plus or minus half the range of your measurements. So if I've got 3 readings, I take the mean, and the mean would be my value, and then I do half of the range, and that would be my uncertainty. So if I had, for example, 3, 4, 5, my mean average, it's always good to state mean average when you're doing exam questions. My mean average would be 4, so it's 3 plus 4 plus 5 divided by 3. And my uncertainty would be half of the range. So we've got 3 or 5 minus 3 over 2. So in this case it's plus or minus 1 for the uncertainty in that range of repeated results. The next thing I'd like to talk about is getting into proper names for uncertainty. So the first one we've got is an absolute uncertainty. And you know you've got an absolute uncertainty because it has the same units as the measurement. The symbol that we're going to use for an absolute uncertainty is delta, so change in. It could be x, could be y, could be r for resistance, or n for newtons, could be anything. So that delta, that's our change in, that's our uncertainty. So if we have an example, if I had a reading on a thermometer of 5.0 degrees, then it's probably the case that we've got plus or minus 1 of the smallest power of 10, the smallest decimal, and then it's going to be degrees C for that one. So the way we state it is we have our value, say x, plus or minus the absolute uncertainty, and then at the end the unit. You might have a really large value, so if you've got a really large value, say a reading of 5,000 newtons, so you might have 5.0 plus or minus 0.1 times 10 to the 3. So that means that both your value and your uncertainty are times 10 to the power 3 newtons. So different ways to express an answer using an absolute uncertainty. We always want to end up with an absolute uncertainty. The guidance from AQA says that the absolute uncertainty should have the same number of decimal places as the measured value. So if I've got a value like 7.819 plus or minus, I need the same number of decimal places. So I could have 0.012. So I've got 3 decimal places here, 3 decimal places here. The size of this, that could be half a range of repeated results. So that could be any size, but the number of decimal places, I don't know, let's go with meters. The number of decimal places should be the same, and you always need to have units afterwards, unless you've got a dimensionless quantity. Okay, the final thing for this video is percentage uncertainty. We're going to need absolute and percentage uncertainties when we get to the next video. Now I'm going to use the notation that we looked at in the last section about absolute uncertainties. So to calculate a percentage uncertainty, we find out what fraction of our value our uncertainty is. We can leave it as a fractional uncertainty, but what we tend to do is times it by 100% to find out what the percentage uncertainty is. Now, what I'm going to do in terms of notation is I'm going to keep it as an uncertainty, but we're going to put a percentage sign down there. So that says to me the percentage uncertainty in x. Okay? What we really need to do is, if we have a value and a percentage uncertainty, so if I had a value of 10 meters with a percentage uncertainty of 10%. Yep. What I need to do is convert back from a percentage uncertainty to an absolute uncertainty in order to express my final answer. So in this case, we need to take our value, divide it by 100, and then times it by your percentage uncertainty. And that will give you back your absolute uncertainty. And if you want to do that at home, you can take this equation here, you can rearrange it to find this, and you'll find that you get your value. So the way I think about it is your value divided by 100 tells you what 1% is, and then you times it by how many percent you've got, and that gives you your absolute uncertainty. So in our example, we've got 10 meters divided by 100 multiplied by 10%. In this case, you can see that 10 times 10 is 100, and then we're dividing by 100. So our uncertainty is 1. So our final answer would be expressed as 10 plus or minus 1 meter. So again, we've got no decimal places, so we're in the units column if you think of it like that. So we're in the units column here as well. I hope that was useful. Leave any feedback in the comments, and I'll get going with our more complicated uncertainties video next. Thank you very much.